Welcome to the Tencent Cloud AI Practitioner course. Over the next several hours, we will build a structured understanding of artificial intelligence, starting from foundational machine learning principles and moving all the way to hands-on enterprise tools like TI1, CodeBuddy, and WorkBuddy. This is not an abstract lecture series. Every concept we cover is anchored in real-world use cases that professionals across IT, product, and business functions encounter every day. By the time we finish, you will be equipped to evaluate, implement, and communicate AI solutions with genuine clarity and confidence. Whether your role is technical or strategic, this course was designed to give you a working command of the Tencent Cloud AI ecosystem. Before diving into the content, let me walk you through the 5 core learning objectives that structure this course. First, you will master the fundamental concepts of AI and machine learning, the vocabulary and mental models every practitioner needs. Second, you'll gain a deep understanding of large language models, with a focus on Tencent Hunyuan. Third, you will learn to implement and integrate Tencent Cloud AI SaaS services into real applications. Fourth, you will get experience with TI1 for model training and deployment. Fifth, you will explore CodeBuddy and WorkBuddy to see how AI reshapes developer and enterprise productivity. Each objective builds on the previous, creating a clear progression from theory to practice. The emphasis throughout is on applied competency, skills you can exercise from day one on the job. This course was designed with 5 distinct professional profiles in mind. IT professionals managing infrastructure who are transitioning into AI-adjacent roles will find the technical grounding they need. Software developers will gain the skills to weave AI capabilities into their applications and enhance existing software solutions. Business analysts and data professionals will learn to extract richer insights using AI tools and drive data-informed decisions. Students and early career candidates will build an industry-relevant foundation and gain practical experience. Enterprise decision-makers will acquire the strategic vocabulary and technical context to evaluate AI investments and transformation initiatives with confidence. Regardless of your current role or background, this course provides a structured, accessible path into the Tencent Cloud AI ecosystem. If you see yourself in any of these categories, this course was built with you in mind. This slide maps out what you will be capable of doing by the end of each module, framed as practical competencies rather than abstract knowledge. Module 1 gives you the conceptual foundation to speak confidently about AI and machine learning algorithms. Module 2 takes you into the architecture of Hunyuan and teaches API integration. Module 3 covers ready-to-use AI services, including OCR, NLP, and speech, and how to integrate them into real business workflows. Module 4 provides hands-on experience with TI1's full model development lifecycle, from data preparation through deployment and monitoring. Modules 5 show how AI tools like CodeBuddy and WorkBuddy transform the daily realities of software development and enterprise knowledge work. Together, these 5 modules create a progression from understanding AI to building with AI. Here is the course roadmap, your navigation guide for the next few sections. We have 6 modules totaling approximately 110 pages. Module 1 covers AI and ML fundamentals, building your conceptual foundation. Module 2 is the most theory-intensive module on LLM and Hunyuan. Module 3 covers Tencent Cloud SaaS AI services. Module 4 is the hands-on TI1 platform module. Module 5A introduces CodeBuddy. Module 5B closes with WorkBuddy and ADP. Think of this roadmap not just as a schedule, but as a map of the modern AI practitioner knowledge domain. From foundational algorithms to large language models, from API-based services to full custom training pipelines, and finally to AI tools that reshape daily work, every module stands independently and reinforces the others. We are now entering Module 1, the AI and ML Fundamentals section. This module is the conceptual bedrock for everything that follows. If you find the later modules on Hunyuan APIs or TI1 Model Training Abstract, come back here. The vocabulary and mental models you build in Module 1 will make the rest far more accessible. We have 3 core goals. First, understand the distinctions between AI, machine learning, and deep learning. Second, explore the 4 major learning paradigms and understand when each is most appropriate. Third, build intuition about how neural networks are structured and why they work. The only prerequisite is a basic familiarity with programming concepts, though you can engage fully with the ideas even without it. What exactly is artificial intelligence? At its core, AI refers to technology that enables machines to simulate human cognitive processes, including learning from experience, reasoning from data, and adapting to new situations. This definition is intentionally broad because AI is an umbrella concept spanning a wide spectrum of techniques. In your daily life, AI is already everywhere. Every time you ask a voice assistant a question, receive a personalized recommendation on a streaming platform, or benefit from predictive navigation in traffic, you're interacting with AI systems. In the enterprise world, AI is transforming process automation, predictive analytics, and customer engagement. The historical arc is equally striking. From Turing's 1950 foundational thesis through Deep Blue's 1997 chess victory, AlexNet's 2012 visual recognition breakthrough, AlphaGo's 2016 triumph in Go, to ChatGPT's 2022 arrival that reshaped global expectations about what AI can do. Each milestone marks a genuine expansion of machine capability. Artificial intelligence represents the broadest domain, encompassing any technique that enables machines to simulate human intelligence, including reasoning, decision-making, and problem-solving. It ranges from simple rule-based systems to highly complex models. Within this domain, machine learning focuses on developing algorithms that can automatically learn patterns from data and improve their performance over time without being explicitly programmed. These models rely on statistical methods and are widely used in areas such as fraud detection, recommendation systems, and predictive analytics. Going further, deep learning is a specialized subset of machine learning that leverages multi-layered artificial neural networks to process large volumes of complex and unstructured data, such as images, audio, and natural language. Deep learning models are capable of capturing intricate patterns and representations, making them highly effective for tasks like image recognition, speech processing, and generative AI applications, such as ChatGPT. In practice, deep learning is supported by powerful frameworks like PyTorch, TensorFlow, and PaddlePaddle, which provide scalable tools for building, training, and deploying models efficiently. Understanding this hierarchy helps clarify how different AI technologies are related and applied in real-world systems. Machine learning generally falls into 4 types. Supervised learning uses labeled data to train models for prediction tasks. Unsupervised learning finds patterns in data without predefined labels. Semi-supervised learning sits in between, using limited labeled data to guide learning across larger data sets. Reinforcement learning is different. It trains an agent through trial and error, using rewards and penalties to improve decisions. These four approaches form the foundation of modern AI systems and are widely applied across industries, from finance and healthcare to gaming and automation. Choosing the right type depends on data, use case, and desired outcomes. This slide introduces key concepts in artificial intelligence and machine learning. A model is a function learned from data that maps inputs to predictions. Features are the measurable variables extracted from raw data that directly influence model performance. Logistic regression is a widely used algorithm for binary classification tasks, such as risk assessment and decision-making. It is important to be aware of overfitting, where a model learns noise and detail from training data, reducing its ability to generalize to new data. Finally, association rule mining helps uncover hidden relationships between variables, commonly used in recommendation systems and user behavior analysis. Supervised learning is the most widely applied paradigm in machine learning and the foundation for most of the AI services we will explore in later modules. The idea is direct. You train a model on labeled examples, where each input has a known and correct output. The model learns to approximate the mapping function between input and output by minimizing prediction errors across a large training set. Think of it as working through an exercise book where every question has an answer key. The model improves through repetition and correction. There are two main task types. Classification predicts discrete categories: spam or not spam, cat or dog, fraud or legitimate transaction. Regression predicts continuous numerical values: house prices, demand forecasts, or patient risk scores. The power of supervised learning is that once trained on representative data, the model can generalize accurately to inputs it has never seen before. This ability to generalize, rather than simply memorize, is what makes trained models genuinely useful in production. Unsupervised learning works with unlabeled data. There are no correct answers to guide the training process. The algorithm must discover structure, patterns, and groupings entirely on its own. This makes unsupervised learning particularly valuable in real-world settings where labeled data is scarce or prohibitively expensive to produce. The three primary techniques are clustering, dimensionality reduction, and association rule mining. Clustering algorithms like k-means group similar data points together, discovering natural segments within a dataset. This is widely used for customer segmentation, anomaly detection, and document organization, allowing businesses to discover meaningful population structures without predefined categories. Dimensionality reduction compresses high-dimensional data into lower-dimensional representations, preserving key information for visualization and as a pre-processing step for other models. Association rule mining finds co-occurrence patterns across datasets, powering the classic customers who bought this also bought that recommendation logic in e-commerce. Unsupervised learning trades the requirement for labeled data for greater need of domain expertise in interpreting and validating results. Reinforcement learning is the most conceptually distinctive of the three major learning paradigms, and arguably the one that most closely mirrors how biological intelligence develops. The core framework involves an agent that takes actions in an environment, receives reward or penalty signals based on those actions, and over thousands or millions of iterations learns to maximize cumulative reward. Think of how a child learns to walk. There is no labeled dataset of correct walking movements. The child tries, falls, receives negative feedback, adjusts, and eventually discovers a stable strategy through pure trial and error. AlphaGo is the most celebrated example of reinforcement learning in practice. By playing millions of games against itself, it developed Go strategies that surpassed the best human players in history. In industry, RL is applied to robotic manipulation, autonomous driving decision-making, and long-horizon recommendation optimization. Unlike supervised and unsupervised learning, reinforcement learning generates its own training signal through environmental interaction, making it particularly powerful for sequential decision-making problems. Semi-supervised learning bridges the gap between supervised and unsupervised approaches by combining a small amount of labeled data with a large pool of unlabeled data. In practice, this matters enormously. Labeling data is expensive and time-consuming, requiring human expertise, domain knowledge, and often specialized tooling. Unlabeled data, by contrast, is abundant and low cost. Semi-supervised learning exploits this asymmetry effectively. The most common approach is self-training. You start with a small labeled data set to build an initial model. Then use that model to generate pseudo-labels for unlabeled examples where the model's confidence is high. These pseudo-labeled examples are added to the training set, and the model is retrained iteratively, steadily improving. A compelling real-world application is medical imaging. Labeling CT or MRI scans requires expert radiologists, making large annotated data sets prohibitively expensive. Semi-supervised approaches allow research institutions to build high-quality diagnostic models using a fraction of the labeled data they would otherwise need, without sacrificing too much in performance. This slide compares the three main types of machine learning. Supervised learning uses labeled data and is best for prediction and classification tasks with moderate complexity. Unsupervised learning works with unlabeled data to discover patterns, but typically requires higher computational effort. Reinforcement learning is the most complex, relying on environment feedback like rewards and penalties, and is used for decision-making scenarios such as robotics or game AI. When choosing the right approach, consider three key factors: data availability, the type of problem you're solving, and the compute resources required. These factors help determine the most suitable and efficient machine learning method. To understand neural networks, we start with the most fundamental unit, a single artificial neuron. Its computation is elegant in its simplicity. A neuron receives multiple input values, labeled X. Each input is multiplied by a corresponding weight W, which represents how much influence that input has on the output. A positive weight amplifies the input's effect. A negative weight suppresses it. A weight near zero makes the input largely irrelevant. These weighted inputs are summed together, and a bias term B is added. The bias functions as an offset, allowing the activation function to shift along the input axis and providing the model with greater expressive flexibility. This weighted sum is then passed through an activation function F, which introduces the nonlinearity essential for learning complex patterns. Without activation functions, stacking multiple layers would still only compute a linear function. The complete expression is y equals f applied to the sum of xi times wi plus b. Every sophisticated deep learning model in existence is built from billions of these simple units. A single neuron is limited in its representational power, but when we organize thousands or millions of neurons into interconnected layers, we create a neural network capable of learning extraordinarily complex functions. The standard feed-forward architecture has 3 layer types. The input layer receives raw data, with one neuron per feature, per pixel in an image, or per token in text. Data flows in at this layer without any computation. Hidden layers are where the actual learning happens. Each layer applies nonlinear transformations to progressively extract more abstract feature representations. For image data, early layers detect edges and textures. Middle layers detect shapes and compositions, and the deepest layers detect high-level semantic concepts like object identities. The network's learned knowledge is encoded in the weights of hidden layer connections. The output layer produces the final prediction. For classification, each output neuron represents the probability of a particular class. For regression, a single continuous value is produced. Training involves repeatedly adjusting all weights through backpropagation to minimize the gap between predicted and true outputs. Activation functions are what give neural networks their nonlinear expressive power, and selecting the right one has direct practical consequences for training stability and model performance. Without activation functions, no matter how many layers you stack, the entire network can only compute linear transformations, fundamentally limiting what it can learn. The four most important activation functions each have distinct properties. ReLU, or rectified linear unit, outputs 0 for negative inputs and the input value for positive inputs. Its computational simplicity and ability to resist the vanishing gradient problem make it the default choice for hidden layers in modern deep networks. Sigmoid squashes any real number into the range 0 to 1. It is used in binary classification output layers, but saturation at the extremes causes gradient vanishing in deep networks, limiting it. The distinction between shallow and deep neural networks is not simply about architecture depth. It represents a qualitative leap in representational capability. Shallow networks with 1 or 2 hidden layers are capable learners, but generally require carefully hand-engineered input features. Engineers must decide which aspects of the raw data to encode, a process that is expensive, domain-specific, and inherently limiting. Deep networks, by contrast, perform automatic feature extraction. They learn hierarchical representations directly from raw data, with each successive layer discovering progressively more abstract patterns. For visual data, early layers detect edges and local textures. Middle layers compose these into shapes and regions, and deep layers detect high-level semantic concepts. This end-to-end learning eliminates the need for manual feature engineering and has produced breakthrough results in computer vision, speech recognition, and natural language processing. It is also the architectural foundation on which every modern large language model is built. The trade-off is that deep networks require substantially more data and compute to train effectively. Decision trees are among the most interpretable machine learning algorithms available, and understanding them well also prepares you to appreciate the more powerful ensemble methods that build on them. A decision tree works by recursively splitting data based on feature conditions, creating a branching structure that closely mirrors human decision logic. Starting at the root, each internal node tests a feature condition, and data follows the appropriate branch. Leaf nodes produce the final predictions. In a credit approval context, the tree might first ask whether the applicant's income exceeds a threshold, then check employment duration, then assess credit history, each split narrowing the prediction toward approval or rejection. The primary advantage of decision trees is interpretability. Any stakeholder can trace exactly why a specific prediction was made by following the decision path, which is invaluable in regulated industries like finance and healthcare. The primary limitation is overfitting. Trees grown too deep tend to memorize training data noise, producing models that perform well on training sets but poorly on new data. Techniques like pruning and maximum depth constraints mitigate this risk. Random forest addresses the fundamental weakness of individual decision trees, their tendency to overfit training data. The underlying principle is ensemble learning, a large collection of diverse, independently trained weak models can collectively produce predictions that are more accurate and more stable than any single model. The construction process has 3 steps. Bootstrap sampling creates multiple distinct training subsets by sampling the original dataset with replacement, ensuring each tree sees a slightly different view of the data. A decision tree is then independently trained on each subset. Crucially, at each split, only a random subset of features is considered. This is what drives the diversity between trees, preventing them from converging on the same patterns. Finally, predictions are aggregated across all trees by majority vote for classification or by averaging for regression. This dual injection of randomness in both data sampling and feature selection creates a forest where each tree is slightly wrong in different ways, but collectively highly accurate. Random forest is one of the most reliable off-the-shelf algorithms for tabular data classification and regression tasks. Support vector machine approaches classification from a geometric perspective. Rather than simply finding any boundary that separates classes, SVM searches for the maximum margin hyperplane, the decision boundary that maximizes the distance to the nearest data point of each class on both sides. This maximum margin objective is what gives SVM its strong generalization properties. The boundary avoids being too close to any training example, reducing sensitivity to noise and improving performance on unseen data. The data points closest to the decision boundary are called support vectors, and they're the only samples that determine where the boundary is placed. The rest of the training data has no influence. When data is not linearly separable in its original feature space, the kernel trick implicitly maps data to a higher dimensional space where separation becomes feasible without explicitly computing the high-dimensional coordinates. SVM excels in high-dimensional, small sample settings, particularly text classification and bioinformatics, where its ability to find stable boundaries in sparse, high-dimensional spaces is a significant advantage. Convolutional neural networks are the architecture behind nearly every modern computer vision system, and understanding their structure gives you insight into how AI perceives and interprets visual information. The CNN's key innovation is the use of convolutional operations, learnable filters that slide across the input image, detecting local spatial patterns through shared weights. This weight sharing dramatically reduces the number of parameters compared to fully connected networks, while preserving the spatial structure of the input. The CNN pipeline has 3 key stages. Convolutional layers apply filters to produce feature maps, detecting progressively more complex patterns as network depth increases. Early layers detect edges, colors, and simple textures. Deeper layers detect shapes, compositions, and eventually semantic level concepts. Pooling layers reduce spatial resolution, extracting the most prominent features while building spatial invariance, the ability to recognize a pattern regardless of where it appears in an image. Fully connected layers aggregate these spatial features into a probability distribution over classes. CNNs are the dominant architecture for image classification, object detection, and facial recognition. Recurrent neural networks were designed specifically for sequential data, any domain where the order of inputs carries meaning, including text, speech waveforms, and time series. The defining innovation in RNNs is the hidden state, a vector that is updated at each time step as the network processes the sequence. This hidden state acts as a form of memory, carrying forward contextual information from earlier positions to inform the processing of later ones. At each step, the RNN combines the current input with the previous hidden state to produce a new hidden state and an output. This recurrent connection creates the temporal dependency that makes RNNs suitable for tasks like machine translation, speech recognition, and sentiment analysis. However, standard RNNs are limited by the vanishing gradient problem. When sequences are long, error signals during backpropagation decay exponentially over time, making it extremely difficult for the network to learn dependencies between positions far apart in the sequence. This fundamental limitation drove the development of LSTM and GRU architectures, and ultimately the transformer architecture, which resolved the problem through a completely different mechanism, self-attention, and became the foundation for all modern large language models. Modern AI systems are powered by three core components: generative models, hardware, and data. Generative AI enables systems to create new content such as text, images, and code directly from user prompts. These models produce human-like outputs and are widely used in applications like chatbots, summarization, and automation workflows. To support these capabilities, specialized hardware is required. GPUs act as the core engine for large-scale parallel processing, making them essential for training deep learning models. CPUs handle system control and support smaller inference tasks, while NPUs are optimized accelerators designed for efficient neural network inference, especially in edge and cloud environments. Finally, data quality plays a critical role. Diverse datasets improve generalization across different scenarios, while clean and consistent data ensures stable and accurate predictions. In contrast, incorrect or noisy labels can significantly degrade model performance. This slide shows how different machine learning approaches are applied in real-world scenarios. For example, email spam filtering uses supervised learning, where models are trained on labeled data to classify emails as spam or not. Customer segmentation uses unsupervised learning to group users based on behavior patterns without predefined labels. In gaming, reinforcement learning is used to train AI agents that learn through rewards and penalties, allowing them to adapt to player strategies. The key takeaway is that each machine learning method solves different types of problems, and the right choice depends on your data and business objective. Let's take a moment to consolidate what we have built in Module 1. We established the conceptual hierarchy, AI as the broadest category, machine learning as a data-driven subset, and deep learning as the neural network-intensive further subset. We surveyed the four major learning paradigms: supervised, unsupervised, semi-supervised, and reinforcement learning, and developed intuition for when each is appropriate. We built a mental model of neural network architecture, from the single neuron computation through to multi-layer deep networks, and understood why activation functions are essential for nonlinear representational power. We examined key algorithms including decision trees, random forests, SVMs, CNNs, and RNNs, and connected each to real-world applications. Every concept from Module 1 is a foundation stone for what follows. Module 2 begins where Module 1 left off, with the transformer architecture that superseded RNNs and gave rise to the large language model era. Let's move forward. Welcome to Module 2, Large Language Models and Tencent Hunyuan. Module 1 established our machine learning foundation. Module 2 takes us into the most consequential AI development of the past decade. Large language models have fundamentally changed how humans interact with computers and are reshaping workflows across industries at an unprecedented pace. In this module, we will address 4 essential questions. What distinguishes LLMs from traditional NLP? What makes the transformer architecture so dominant? How is Tencent Hunyuan architected and positioned? And how do developers integrate Hunyuan into real products? This is the most technically rich module in the course, but every concept connects directly to application. A large language model is a deep learning model built on the transformer architecture and pre-trained on enormous text datasets, capable of understanding, generating, and reasoning about natural language. The key to appreciating what makes LLMs distinctive is understanding the role of scale. Model parameters are the numerical values encoding everything the model has learned. In 2018, BERT with 110 million parameters was a landmark achievement. GPT-3 in 2020 scaled to 175 billion, producing qualitatively different outputs. Today's frontier models operate at hundreds of billions to over a trillion parameters. What is remarkable is that this scale unlocks emergent capabilities not present in smaller models. Multi-step reasoning, code generation, cross-lingual understanding, and strong performance on tasks the model was never explicitly trained for. These emergent properties are one of the defining distinctions of large language models. The pivotal moment in LLM history was 2017, when Google published Attention is All You Need, introducing the transformer. This paper replaced sequential RNN processing with parallel self-attention, enabling training on vastly larger datasets with far greater efficiency. From 2018 to 2019, BERT and GPT emerged as 2 foundational paradigms. BERT uses a transformer encoder to achieve bidirectional understanding of context, while GPT uses a transformer decoder for unidirectional, autoregressive generation. This architectural difference defines their core capabilities. The 2020 to 2022 period was defined by scale. GPT-3, with 175 billion parameters, demonstrated that model performance follows scaling laws, improving predictably as model size, data volume, and compute increase, rather than depending on any single factor alone. From 2023 onward, conversational and multimodal models have become mainstream, with advances in reasoning, multimodal capability, and agentic systems defining the frontier of AI. Training a large language model is a carefully designed multi-stage pipeline. Stage 1 is pre-training, where the model trains on hundreds of billions or trillions of tokens using a next token prediction objective, internalizing language structure, factual knowledge, and reasoning patterns across an enormous corpus. This stage requires thousands of GPUs running for weeks or months. Stage 2 is tokenization, converting raw text into sequences of token IDs that the model processes numerically. Stage 3, the core of pre-training, is the actual next token prediction process, where the model iterates over billions of examples, adjusting weights to improve prediction accuracy. Stage 4 is fine-tuning. Supervised fine-tuning on curated instruction response pairs teaches instruction following behavior, while RLHF aligns outputs with human values for helpfulness, safety, and honesty, transforming a raw language model into a reliable assistant. The transformer architecture, introduced in Attention Is All You Need in 2017, is the foundational innovation behind every major LLM in production today. Its central contribution is self-attention, a mechanism that computes relationships between all positions in a sequence simultaneously, unlike RNNs that process step by step. This parallel processing capability is what makes transformer-based models scalable to sizes required for LLMs. The architecture consists of encoder and decoder stacks. Key components include positional encoding, which injects sequence order, multi-head attention, which enables simultaneous attention across multiple representation subspaces, feed-forward networks for further transformation, and residual connections with layer normalization for training stability. Every LLM you encounter, BERT, GPT Palm, Hunyuan, is built on this foundation. Self-attention is the mechanism at the heart of the transformer. It uses three learned vectors: query, key, and value. Think of it as a soft information retrieval system. The query represents what a position is looking for. Keys advertise what information each position has available. Values contain what each position will contribute when attended to. Attention scores are computed by taking dot products of each query with all keys, scaling to prevent instability, and applying softmax to produce a probability distribution over positions. These scores weight the value vectors in a weighted sum, producing a context-aware representation for each position. Multi-head attention runs this process in parallel across multiple subspaces, simultaneously capturing syntactic dependencies, semantic relationships, and coreference links. The classic example is the animal didn't cross the street because it was too tired. Self-attention correctly resolves it to animal through global attention scores. The transformer's capabilities emerge from the precise coordination of several components. The embedding layer converts tokens into dense vectors where semantically similar tokens are positioned nearby, the numerical foundation for all downstream computation. Positional encoding adds location information since self-attention has no inherent sense of order. It is the mechanism that allows the model to understand word positions in a sequence. Feed-forward networks follow each attention layer, applying nonlinear transformations to enrich representations beyond what attention alone captures. Residual connections pass each layer's input directly to its output, creating gradient shortcuts that solve the vanishing gradient problem in very deep architectures. Layer normalization standardizes activations at each layer, maintaining stable training dynamics throughout the deep stacks characteristic of large language models. Together, these components enable training at dozens to hundreds of layers with consistent effectiveness. Large language models learn general intelligence through large-scale pre-training on massive amounts of unlabeled data, such as web text, books, code, and articles. The key objective is not memorization, but learning patterns in language. The core mechanism is self-supervised learning, where the model predicts the next token in a sequence. For example, given the cat sat on the model learns to predict Matt by optimizing its internal parameters. Over time, this process allows the model to internalize syntax, semantics, and even world knowledge. Importantly, this learning forms a foundational intelligence layer that can generalize across many tasks. Instead of training separate models for each task, one base model can adapt to translation, summarization, reasoning, and more. This is why LLMs are powerful. They learn representations that transfer across domains, making them flexible and scalable for real-world applications. To scale LLMs efficiently, modern architectures rely on two key innovations: multi-head attention and mixture of experts. Multi-head attention allows the model to process information from multiple perspectives simultaneously. Each attention head focuses on different relationships, such as syntax, semantics, or long-range dependencies, before combining them into a unified representation. This improves contextual understanding significantly. On the other hand, mixture of experts introduces sparsity into the model. Instead of activating all parameters, a gating network dynamically selects a subset of expert subnetworks for each input token. This allows the model to scale to trillions of parameters while maintaining computational efficiency. In practice, this means higher performance without proportional increases in cost. Together, MHA improves understanding, while Mo improves scalability. These innovations are critical for building next-generation AI systems that are both powerful and resource-efficient. Turning LLMs into real-world systems requires additional components beyond the model itself. First, the system prompt defines global behavior, tone, and safety constraints, ensuring consistent and controlled outputs. Second, Retrieval-Augmented Generation, or RAG, connects the model to external knowledge sources. Instead of relying only on pre-trained data, the system retrieves relevant information from databases and injects it into the prompt, significantly improving accuracy and reducing hallucination. Third, server-sent events enable real-time streaming responses. Instead of waiting for the full output, users receive tokens progressively, creating a responsive and interactive experience. Together, these components bridge the gap between raw model capability and production-ready AI systems. They ensure that outputs are grounded, safe, and responsive, which is essential for enterprise use cases such as customer support, financial analysis, and security operations. A complete LLM system follows an end-to-end pipeline from user query to streaming output. It begins with the user query, which includes raw text and parameters. This input enters the context assembly layer, where system prompts define behavior and RAG pipelines retrieve relevant knowledge from vector databases. The enriched context is then passed to the LLM engine. Inside the model, components such as multi-head attention and mixture of experts process the input efficiently, generating high-quality responses. Finally, the output is delivered through a streaming mechanism, such as SSE, enabling real-time interaction. This architecture separates concerns clearly. Retrieval handles knowledge, prompts handle control, and the model handles reasoning. Such modular design allows scalability, flexibility, and easy integration with enterprise systems. It also ensures better performance, lower latency, and improved reliability in production. Tencent Hunyuan is Tencent's proprietary large language model and the foundational model layer of the entire Tencent AI ecosystem. Its scale is remarkable. Hunyuan powers over 400 products and business functions across the Tencent portfolio, including WeChat, Tencent Video, and QQ. Architecturally, Hunyuan is built on the Transformer Foundation with a mixture of experts design. Mo uses a routing mechanism to selectively activate only the most relevant parameter subsets for each inference request, maintaining very large total capacity while keeping per-inference computational costs manageable, critical for serving hundreds of millions of users at scale. The infrastructure layer spans over 400 GPU variants, providing the computational foundation for training and serving at enterprise scale. Hunyuan's capabilities are exposed through a unified API platform that developers access via Tencent Cloud. Modern large language models have evolved well beyond text-only processing into multimodal systems capable of understanding and generating across multiple data types. Tencent Hunyuan's multimodal capabilities span image, video, and 3D content modalities. On the image side, Hunyuan supports both image understanding, analyzing visual content and answering questions about it, and image generation, creating high-quality visuals from text descriptions. Video capabilities extend to temporal analysis, key information extraction, and video clip generation for prompts. Three-dimensional content generation allows producing 3D models from text or 2D images, opening applications in game development and product design. The technical foundation is a unified semantic representation space where different sensory modalities are encoded into compatible embeddings, allowing coherent cross-modal reasoning that approaches how humans integrate diverse sensory inputs to understand the world. This slide details the specific capabilities within Hunyuan's multimodal input portfolio. Text capabilities form the foundation. Natural language dialogue, content generation, code understanding, and reasoning. Image capabilities cover scene recognition, object detection, chart comprehension, and visual question answering, enabling applications to genuinely understand visual content. OCR text recognition provides precise character extraction from images, handling both printed and handwritten text across complex layouts, highly relevant for in-voice processing, document digitization, and form automation. Video understanding extracts key information from video clips, recognizes behavioral events, and generates content summaries. This comprehensive multimodal coverage means tasks that previously required multiple specialized models working in pipeline can now be accessed through a single unified integration, substantially reducing system complexity and development overhead. Image generation is one of the most visually compelling capabilities in the generative AI landscape. Hunyuan generates high-quality visual content from natural language prompt inputs. Effective prompts typically combine 3 layers: subject descriptions specifying what should appear in the image, style specifications such as photorealistic, oil painting, or illustration, and technical parameters like resolution and lighting conditions. Technically, Hunyuan's image generation is based on diffusion model architecture, where the model iteratively removes noise from a random initialization until it converges on a result aligned with the text description. This capability has substantial commercial applications in advertising creative generation, product visualization, game art production, and marketing content creation, significantly reducing both the time and cost of visual content production and making high-quality generation accessible to non-designers. Hunyuan provides a standard RESTful API following HTTP protocol and JSON data format, compatible with mainstream development frameworks. The call workflow has 3 steps. First, authentication. Developers obtain secret ID and secret key credentials from the Tencent Cloud Console to sign each request. Second, making the request using HTTPS REST or RPC format, with the body containing the model name, conversation messages, and configuration parameters like temperature. Third, processing the JSON response, which contains generated content, token usage statistics, and request metadata. Practical considerations include rate limits. QPS caps require request queuing and retry logic for high concurrency applications. The standardized API design also reduces migration costs from other platforms, since the interface follows widely recognized conventions compatible with mainstream frameworks. Token Hub is Tencent Cloud's unified large model service platform built for enterprises and developers. Under the hood, we combine our in-house Hunyuan Foundation models with a curated set of premium third-party models, which gives customers both breadth and quality from day one. We wrap 6 high-value AI capabilities into standardized APIs, covering general dialogue, deep reasoning, code generation, visual understanding, image generation, and video generation. Teams no longer need to worry about model selection or low-level deployment. They can plug the APIs directly into customer service, financial analysis, developer productivity, multimodal interaction, marketing campaigns, and short video creation, taking the shortest path from raw model power to real business value. On the commercial side, Token Hub offers 3 composable service modes that map cleanly to different stages and workloads. Pay-as-you-go bills purely on real usage and suits development, testing, and early exploratory workloads where traffic is still volatile, letting teams validate ideas at minimum cost. Reserve capacity pre-allocates compute so latency stays stable and throughput stays predictable under heavy concurrency, making it the default choice for production. Dedicated deployment delivers a fully isolated private environment with end-to-end data control, which is a natural fit for finance, government, and healthcare customers with strict compliance and security requirements. Enterprises can mix and match these modes as their business evolves, turning AI compute into an on-demand utility. This case study highlights how a leading law firm transformed its client service using an AI-powered legal assistant. Traditionally, clients had to wait hours or even days for responses as lawyers manually reviewed cases and drafted replies. This created bottlenecks, high operational costs, and limited scalability. By deploying a Hunyuan-powered legal chatbot integrated with internal knowledge bases and RAG capabilities, the firm enabled 24/7 instant consultation. The system can accurately interpret legal questions, retrieve relevant statutes, and generate draft responses within seconds. Around 80% of routine inquiries are now handled automatically, while complex cases are seamlessly escalated to human lawyers for validation. The results are significant. Response accuracy reached 91%, and customer satisfaction improved to 93 out of 100. This demonstrates how AI can augment, not replace, legal professionals, improving efficiency while maintaining compliance and quality. This case study focuses on Kashibo, an AI-powered education platform designed to process massive volumes of exam questions. The key challenge was handling millions of unstructured question images, including complex formulas, diagrams, and handwritten inputs. Traditional OCR systems struggled with low accuracy and lacked the ability to understand context and logic. To address this, Tencent Hunyuan Vision was introduced, combining advanced OCR with multimodal AI reasoning. The workflow is simple. Students take a photo, upload it to the cloud, and the AI performs deep analysis, extracting text, interpreting formulas, and understanding problem logic. It then generates structured answers with step-by-step explanations. The impact is substantial. Overall processing efficiency improved by 98%, while manual intervention dropped below 2%. This demonstrates how multimodal AI can transform education workflows by delivering fast, accurate, and scalable learning support. Let's consolidate Module 2. We built a systematic understanding of large language models, from the evolution of parameter scale to the emergence of capabilities at scale. We examined the transformer architecture in depth, including self-attention, multi-head attention, and the coordinated role of key components, understanding why this architecture displaced all previous approaches to sequence modeling. We traced the multi-stage training pipeline from pre-training through fine-tuning and RLHF, understanding how a raw language model is transformed into a practical instruction following assistant. We explored Tencent Hunyuan's architecture, model variants, and multimodal capabilities, along with how to integrate Hunyuan through the API. With this foundation, we moved to Module 3 to explore Tencent Cloud's ready-to-use AI SaaS services. How to incorporate AI capabilities into business applications without training your own models. Welcome to Module 3, Tencent Cloud SaaS AI Services. If Module 2 answered what large language models are and how they are trained, Module 3 answers how to use AI without training your own models. Tencent Cloud SaaS AI is a suite of ready-to-use AI capabilities: NLP, OCR, speech processing, vision, and content moderation, accessible through standard APIs and SDKs. Developers integrate these capabilities into business applications within minutes, without infrastructure complexity or model training overhead. This module covers 4 major capability categories: NLP for natural language processing, including sentiment analysis and machine translation; OCR for optical character recognition, including general text and specialized document formats; speech processing, including ASR for speech-to-text and TDS for text-to-speech; and Vision AI, including face recognition and content moderation. Each service area has direct, real-world business case applications. Tencent Cloud SaaS AI follows a standard SaaS service design pattern that provides developers with a clean, unified integration pathway. At the API layer, all AI services are exposed through standard RESTful interfaces with JSON request and response formats, consistent with mainstream development practices and easy to integrate with existing systems. The SDK support layer provides official clients for Python, Java, Node.js, and Go, dramatically lowering the integration threshold. Developers typically complete service calls in just a few lines of code. The AI capability layer contains the full portfolio of continuously updated AI models spanning NLP, computer vision, speech processing, and OCR, with specialized subinterfaces for different scenarios within each domain. The infrastructure layer relies on Tencent Cloud's compute and storage services, CAS object storage, and CVM instances, providing the stable, reliable foundation for all AI service operations. Natural language processing is the field enabling computers to understand, analyze, and generate human language, and it is one of the most broadly applied capability domains within the SaaS AI portfolio. Tencent Cloud's NLP services cover several core language understanding functions. Sentiment analysis detects the emotional orientation, positive, negative, or neutral, expressed in text with confidence scores. This is widely applied to product review analysis, social media monitoring, and customer satisfaction measurement. Text classification categorizes input text according to predefined taxonomy, enabling content filtering, automated ticket routing, and document management. Named entity recognition extracts structured information, people, places, organizations, and dates from unstructured text, serving as the core component for information extraction pipelines. Keyword extraction identifies the most representative terms in text, enabling rapid content summarization. Text similarity calculation quantifies semantic resemblance between text segments, applied to duplicate detection and question-answer matching. Sentiment analysis is one of the most commercially actionable NLP capabilities. Tencent Cloud's Sentiment Analysis V2 interface classifies input text into positive, negative, and neutral sentiment polls, providing confidence scores for each. These scores are probability values between 0 and 1, with higher scores indicating greater model confidence in that sentiment classification, and all three scores summing to 1. In a practical example, a user review expressing enthusiasm about a restaurant experience would receive a positive confidence score near 0.98, with minimal scores for neutral and negative. In business applications, sentiment analysis is widely used for e-commerce platform review analysis, enabling operations teams to quickly gauge overall consumer satisfaction trends. It powers social media monitoring for brand reputation tracking, and it supports customer service quality assurance by detecting negative sentiment conversations that should trigger agent intervention. Optical character recognition converts text within images into editable digital formats and is one of the most broadly applicable capabilities in the Tencent Cloud SaaS AI portfolio. Tencent Cloud's OCR services cover the full spectrum from general purpose to highly specialized scenarios. General text recognition handles most printed and handwritten text and images, extracting both content and positional information, the fundamental OCR capability for diverse document types. Specialized recognition services are deeply optimized for specific ID card recognition is one of the most frequently used specialized OCR capabilities in the Tencent Cloud portfolio. It automatically identifies and extracts all key fields from identity card images: name, gender, ethnicity, date of birth, residential address, and ID number, returning results in a structured JSON format that can be directly written to business databases without manual reentry. The service accepts JPG, PNG, and PDF format inputs and includes anti-forgery detection capabilities that identify photocopies and screenshots rather than original documents, providing an additional layer of security for scenarios requiring genuine document verification. In business applications, this service is widely deployed in financial institution account opening workflows, e-commerce platform real name verification, rental industry tenant background checks, and any online service requiring user identity confirmation. Automated ID recognition dramatically improves user registration and authentication efficiency while reducing manual input errors, representing significant labor cost saving for platforms processing large volumes of user verifications. Invoice recognition is among the most financially impactful specialized OCR capabilities for enterprise clients. Traditional invoice entry workflows are highly dependent on finance staff manually verifying and entering data, creating both efficiency bottlenecks and error risks. A significant operational burden for organizations processing high volumes of invoices. Tencent Cloud's Invoice OCR supports standard VAT invoices, special VAT invoices, and electronic invoice formats, precisely extracting invoice codes, invoice numbers, issuance dates, line item details, and total amounts including tax, and outputting in structured JSON format for direct integration with enterprise financial systems. The typical automated workflow has 4 steps. Employees photograph or scan invoice images and upload. The OCR engine extracts all fields, The system automatically validates amounts and categories against reimbursement policies, and compliant invoices enter the approval pipeline directly. This automated chain reduces invoice processing time from minutes to seconds while dramatically lowering error rates, delivering substantial annual labor cost savings for high-volume organizations. Business card recognition is a compelling application of OCR in enterprise contact management and customer relationship contexts. Traditional business card information entry relies entirely on manual input, a time-consuming and error-prone process at business events and conferences where large numbers of cards are exchanged. Tencent Cloud's business card OCR automatically identifies and structures all key information from card images: name, title, company, phone, email, and address, returning normalized, structured data formats. Compared to manual entry, recognition is virtually instantaneous and eliminates transcription errors. The typical application workflow has 3 steps. Step 1. Capture the business card image via mobile device or scanner. Step 2. The AI recognition engine extracts and structures all fields. Step 3. Output the structured data in JSON format and write to the CRM system or contacts database. This workflow allows sales professionals to complete digital archiving of card information within seconds of a meeting rather than spending time on manual entry at the end of the day, directly improving the data completeness and timeliness of customer relationship management. Tencent Cloud OCR services cover a wide range of application scenarios. In standard OCR scenarios, general text recognition, table recognition, and handwriting recognition provide foundational digitization for diverse document types. In specialized OCR scenarios, dedicated interfaces for identity documents, ID cards, driver's licenses, passports, and financial documents, invoices, bank statements, provide deeply optimized field extraction. In AI-enhanced scenarios, OCR capabilities combine with other AI services for more complex information processing. For example, combining OCR with NLP for automatic contract clause extraction or with security services for document authenticity verification. In super-resolution scenarios, image enhancement technology processes low-quality, blurred images to improve recognition accuracy. A particularly valuable capability to highlight is PS detection, which identifies whether images have been digitally manipulated, carrying important fraud prevention value in financial and government application contexts. Automatic speech recognition converts spoken audio into text and forms the core of voice AI services. Tencent Cloud's ASR achieves recognition accuracy exceeding 97% for standard Mandarin Chinese, supports PCM, WAV, MP3, and other common audio formats, and handles both real-time streaming audio and pre-recorded file scenarios. ASR systems must address 3 technical challenges: acoustic variability from differences in speaker accent, speaking rate, and volume, linguistic complexity including ambiguity, hesitations, and grammatical irregularities, and environmental noise from real-world recording conditions. Tencent Cloud ASR addresses these challenges through multi-layered deep learning model architectures and extensive training on real-world scenario data. The commercial applications are substantial: automated meeting transcription, customer service call real-time transcription, voice search, subtitle generation for video content, and accessibility features for users with hearing or mobility impairments. Real-time ASR is the most technically demanding ASR application mode, requiring speech-to-text conversion within milliseconds as audio streams in, achieving near instantaneous text output. Unlike offline file recognition, real-time ASR must handle continuous audio stream segmentation, dynamic context maintenance, and a balance between high accuracy and low latency under strict timing constraints. Tencent Cloud's real-time ASR uses WebSocket long connections to transmit PCM or WAV format audio streams, with the server continuously outputting intermediate recognition results and confirmed final text as it processes incoming audio. Direct application value exists across several latency-sensitive scenarios: real-time captioning for conference rooms, live streaming subtitle generation, customer service call assistant overlays, and live audio interpretation services for hearing-impaired users. On the technical side, real-time recognition also supports speaker diarization, identifying and labeling which time segments belong to which speaker, which is highly practical for meeting transcription and customer service call analysis. Offline audio file recognition is designed for processing pre-recorded audio files rather than real-time streams. Unlike real-time ASR, where minimizing latency is paramount, offline recognition prioritizes accuracy and completeness, making it appropriate for scenarios with higher tolerance for processing time but stronger requirements for transcript fidelity. Tencent Cloud's offline ASR supports WAV, MP3, M4A, AMR, and other common audio formats, with file submission via Tencent Cloud COS object storage or direct URL. Typical offline ASR scenarios include batch transcription of archived customer service recordings for analysis, converting recorded meeting videos into time-stamped meeting transcript documents, and automated subtitle generation for podcast and video content. The service also supports speaker diarization in offline mode, distinguishing between speakers in the transcription output, particularly valuable for multi-participant meeting recordings and interview audio. The output format includes timestamps and speaker labels, directly usable for generating professional meeting records. Text-to-speech is the complement to ASR, converting written text into natural, spoken audio. Tencent Cloud's TDS service uses deep learning-based speech synthesis technology, offering multiple voice choices, customizable speaking rate and pitch, and output in MP3, WAV, and PCM formats. TDS applications are remarkably broad. In intelligent customer service, TDS provides voice output capability to customer service bots, enabling natural two-way voice interaction rather than relying solely on text interfaces. In content broadcasting, news, announcements, and notification content can be automatically converted to speech for smart speakers, audiobooks, and radio-style formats. In navigation and voice assistance, TDS converts routing instructions and responses to speech in real time. In accessibility applications, TDS delivers screen reading capability for visually impaired users. SSML, the speech synthesis markup language, is the advanced control interface for TDS. Through XML format markup instructions, developers can precisely control pause positions, speaking rate changes, pitch variation, and emphasis patterns to produce professional-grade voice output tailored to specific application requirements. Tencent Cloud TDS offers a rich selection of voice options to meet the sound style requirements of different application scenarios. The standard voice library provides multiple carefully tuned preset voices spanning different genders, age characteristics, and style orientations, directly applicable to the majority of use cases. Ultra-realistic voices further elevate the quality beyond standard options, achieving greater naturalness, emotional expressiveness, and detail fidelity that approaches human speech, appropriate for brand applications with high audio quality requirements like audio advertisements and premium service interfaces. Multi-language support enables TDS to provide a unified voice interface for different language versions of applications, currently supporting standard Mandarin, Cantonese, English, and additional languages. Voice cloning is an advanced TDS capability where the AI model learns and replicates the characteristics of a target voice from short audio samples, then synthesizes arbitrary text content in that voice, uniquely valuable for brand voice consistency programs and personalized assistant applications. SSML support allows developers to use markup language to precisely control synthesis details for professional-grade audio output. Vision AI forms an important segment of the Tencent Cloud SaaS AI service portfolio, covering image recognition, object detection, facial services, and video analysis capability domains. Image recognition understands the content of images, identifying scene types, object categories, and visual attributes, applicable to e-commerce product categorization and content tagging workflows. Object detection goes beyond identification to precisely localize each object within an image using bounding box coordinates, enabling intelligent surveillance and industrial quality inspection applications. Facial services span multiple capability levels: face detection, face recognition with both one-to-one comparison and one-to-N search, liveness detection to prevent spoofing, and face attribute analysis. These are core technical components for financial real-name authentication and access control systems. Video analysis supports content understanding, tag generation, and abnormal event detection for streaming platforms and security systems. All of these Vision AI capabilities are accessible through standard APIs, enabling developers to rapidly integrate computer vision into applications without needing to train and deploy their own visual models. Visual Product Search is one of the most commercially impactful computer vision applications in retail and e-commerce. Instead of typing keywords, shoppers upload or snap a photo, and the system retrieves visually similar items from the catalog in milliseconds, breaking the language and description barrier that often blocks conversion. Tencent Cloud's Visual Product Search lets merchants build their own feature library indexing tens of millions to billions of product images, and supports multi-view matching that is robust to occlusion, deformation, and lighting changes. The typical pipeline has 3 stages. The query image is uploaded, a deep vision model extracts a high-dimensional feature vector, and an ANN index returns the top similar products ranked by similarity. In production, this capability powers find similar carousels, snap-to-shop features, cross-platform anti-counterfeit monitoring, and visual merchandising workflows. The business value is direct. Higher click-through on long-tail SKUs, shorter discovery paths, and measurable lift in GMV. Video AI handles dynamic visual content as the complement to static image processing, supporting deep content understanding and event analysis on video data. Critical technology for streaming platforms, security systems, and content moderation workflows. Video content recognition analyzes frame sequences to understand scene types, object categories, and human actions, generating tags and summaries that enable automated classification and indexing of large video libraries. Video quality analysis evaluates sharpness, brightness, and noise levels, providing quality control signals for content review and upload pipelines. Intelligent cover extraction automatically selects the most representative frames as thumbnails, replacing manual selection and improving content presentation efficiency. AI moderation combines video AI with content safety services, enabling automatic detection of policy-violating content through frame-level content understanding, essential for UGC platform compliance operations. Video timeline analysis performs segmented understanding of long-form videos, locating timestamps for specific events and key content. Applicable to surveillance video event retrieval and structured analysis of long-form content. Content moderation addresses the compliance operations need of any platform hosting user-generated content, enabling rapid automated identification and handling of policy-violating content at scale to maintain a healthy content ecosystem. Tencent Cloud Content Moderation implements a three-tier review architecture that forms an efficient content processing pipeline. The AI initial review tier automatically analyzes text, image, and audio content, identifying violations across categories including adult content, violence, spam, and policy-sensitive material, and assigning confidence scores to each. High-confidence clear violations are blocked immediately. Low-confidence ambiguous content is passed to the next tier. The policy rules tier applies configurable filters for further screening, supporting custom keyword lists and industry-specific rule configurations. The human review tier handles the ambiguous content that AI cannot definitively classify, with human annotations fed back to the AI models to create a continuous improvement loop. This three-tier system dramatically reduces manual review workload while maintaining strong interception capability, essential infrastructure for large content platforms. This slide illustrates the end-to-end workflow of face recognition in real-world applications through a simple three-step process. The first step is image acquisition, where user's face is captured using cameras or mobile devices, either in real time or via uploaded images. Image quality is critical, so this stage often includes quality checks and user guidance. The second step is face analysis. The captured image is sent to a recognition service, which performs face detection, feature extraction, and liveness detection. It then compares the extracted features with stored face data and returns a similarity score and result. The final step is business decision-making, where the application determines whether to grant access, complete authentication, or trigger further verification. This workflow is widely used in banking, access control, attendance systems, and hospitality services. This section reviews key AI application concepts and tests your understanding. In computer vision, OCR pre-processing is essential for improving recognition accuracy. Techniques such as denoising, skew correction, and text region detection help handle complex backgrounds and ensure better results. In speech processing, speaker diarization is used to distinguish between different speakers within an audio stream, which is critical for meeting transcription and call analysis. To further improve speech recognition in noisy environments, techniques like noise suppression and beamforming are applied to enhance audio clarity. Voice cloning represents another advanced capability, allowing systems to replicate a speaker's voice and generate new speech content with similar characteristics. Finally, in face recognition, it is important to understand the difference between verification and search. 1:1 verification confirms identity, while 1 in search matches against a database. These concepts are fundamental in real-world AI applications. Before moving to case studies, let us cover a set of integration best practices that separate toy demos from production-grade SaaS AI deployments. First, API key management. Never hardcode secret ID and secret key in source code or commit them to Git. Use environment variables or a secrets manager. Rotate keys on a schedule and apply least privilege so each key only has access to the services it actually needs. Second, robust error handling and retries. AI APIs occasionally return timeouts, rate limit errors, or transient failures. So wrap every call with exponential backoff, a circuit breaker for downstream degradation, and clear fallback behavior for the end user. Third, batch and stream appropriately. Many services support batching to cut per call overhead and streaming for lower perceived latency. And choosing the right pattern can reduce cost and latency by an order of magnitude. Fourth, monitor usage and cost. Track QPS, latency, error rate, and spend per service per environment, and set alert thresholds before the monthly invoice surprises anyone. Finally, cache aggressively for idempotent queries and design for graceful degradation so a transient AI outage does not take down the whole product. This banking case shows how Tencent Cloud OCR compresses days of manual work into minutes while lifting data accuracy. The bank's customer onboarding and loan workflows were entirely paper-driven. ID cards, bank statements, payslips, and property certificates had to be keyed in by hand, creating a compounding mix of long turnaround times, high error rates, and rising operational cost. The solution paired Tencent Cloud Smart Structured OCR with card and receipt recognition, so any document type could be auto-classified and the right extraction model applied without manual sorting. The service extracts every key field: name, ID number, account number, amount, and date in a structured JSON that the core banking system ingests directly. Results were immediate. Data extraction accuracy reached 99%. Processing time collapsed from several days to a few minutes, and the review team shifted from data entry to exception handling. For the bank, this is not just efficiency, it changes the customer experience, because onboarding and loan approval that used to feel slow now feel close to real time. This e-commerce case illustrates how LLM-powered chatbots absorb peak season support volume that would otherwise overwhelm a human team. During large promotions, ticket volume can spike 10 to 20 times normal, creating long wait times, frustrated customers, and burnout agents. The platform deployed a Hunyuan-based chatbot grounded in its product catalog, order database, and policy documents, handling high-volume intents like order status, return eligibility, logistics tracking, and coupon usage. For anything the bot cannot resolve confidently, or anything emotionally charged, it hands off to a human agent with the full conversation context already attached, so the agent does not start from scratch. The outcome is a clear efficiency and experience uplift. First response time drops from minutes to seconds. 70% or more of standard queries are fully auto-resolved, and human agents focus on complex or high-value conversations where judgment actually matters. The pattern here, RAG on enterprise data plus a clean escalation path, is the blueprint for almost every customer-facing LLM deployment. Let us consolidate Module 3. We have systematically covered the full capability portfolio of Tencent Cloud SaaS AI services, illustrated through concrete business cases showing how these capabilities create value in real operational contexts. We explored NLP services, sentiment analysis, entity recognition, and machine translation, understanding how language processing technology enables broad application in content analysis and language services. We went deep on OCR services, from general text recognition to specialized invoice and document formats, seeing how document digitization serves as foundational infrastructure for enterprise efficiency. We examined speech services, ASR and TDS, and how they combine into complete voice interaction solutions. We covered vision AI and content moderation and their roles in production business contexts. All of these services are available through unified APIs and SDKs, enabling rapid AI capability integration without model development from scratch. With this foundation, we enter Module 4 to explore TI1, Tencent's platform for enterprises that need custom-trained AI models for specialized requirements. Welcome to Module 4, the TI1 training platform. The first 3 modules gave us AI, theoretical foundations, and access to Tencent Cloud ready-to-use services. But in enterprise practice, off-the-shelf services often cannot fully meet specialized business requirements. Enterprises need to train proprietary models on their own data to achieve the precision and domain specificity their workflows demand. TI1 is designed precisely for this. A fully managed machine learning platform providing complete MLOps workflow support from data preparation through model training, evaluation, deployment, and monitoring. This module covers TI1's core functional areas, including the notebook development environment, AutoML, distributed training, model deployment, and online inference and model monitoring, with real business case illustrations. This is the architectural view of the TI1 platform, and it is worth studying carefully because every capability we cover later maps back to one of these layers. At the bottom sits the Tencent Cloud infrastructure, CPU and GPU pools scheduled through TKE, high-performance cost storage, and low-latency container networking, providing elastic compute at any scale. The data preparation layer handles ingestion, annotation, and feature engineering, turning raw inputs into training-ready datasets with full version control. The model training and evaluation layer is where the real machine learning happens. Built-in algorithms, distributed training, AutoML, and hyperparameter optimization, and support for fully custom containers when teams need total control. Above that, the model registry stores every trained artifact with its lineage, metrics, and approval status, feeding the deployment and inference layer where models go live as online APIs or batch jobs. This layered separation is what allows TI1 to serve both exploratory notebook work and hardened production pipelines from a single platform. The workspace is where project management, collaboration, and resource allocation come together, and it is the day-to-day surface most users interact with. Each project gets its own isolated workspace, grouping notebooks, datasets, training jobs, models, and deployments, so the full life cycle is visible in one place rather than scattered across tools. Role-based access control means data scientists, engineers, and reviewers each see exactly the resources they need, no more, no less, which matters when sensitive training data or production models are in play. Shared storage buckets and notebook environments let team members hand off work cleanly, while experiment tracking records every run so reproducibility is a feature, not a forensic exercise. Resource allocation is flexible. Teams can reserve dedicated GPU pools for heavy training or fall back to on-demand compute for exploration, and quotas prevent one project from starving the others. Think of the workspace as the organizational unit of TI1. Get this layer right, and everything downstream becomes easier. Notebook is the most central interactive development environment in TI1, built on the widely adopted JupyterLab platform that supports the mixed presentation of code, documentation, visualizations, and execution results. Ideal for exploratory data analysis and iterative model experimentation. TI-1's notebook adds cloud-specific optimizations on top of standard JupyterLab. For compute configuration, users flexibly select CPU or GPU instances and switch between sizes without interrupting work. Framework support provides TensorFlow, PyTorch, Mindspore, and major scientific computing libraries pre-installed and ready to use, eliminating environment configuration overhead. For resource management, instances can be stopped and restarted without losing code or data, avoiding wasteful idle compute. Dockerized runtime environments ensure experiment portability, allowing team members to share identical configurations for reproducible results. The model registry is the single source of truth for every trained model in the organization, and it is what makes serious production ML possible. Every model version is stored with its full metadata, training dataset, hyperparameters, evaluation metrics, framework, and the commit hash of the training code, so you can always answer the question of exactly what is running and how it got there. Version control lets you compare performance across iterations side by side. And if a new version regresses in production, rollback is a single click rather than a rebuild. The registry also enforces the governance layer most enterprises need. Approval workflows for promoting a model from staging to production, signed-off reviewers, and automated policy checks for bias or safety constraints before a model can go live. Downstream systems, online inference, batch jobs, edge deployments, all pull from the registry rather than from arbitrary file paths, which eliminates the classic problem of not knowing which model is actually serving traffic. AutoML, automated machine learning, is TI-1's intelligent toolset for reducing the ML expertise barrier by automating the most time-consuming and experience-dependent phases of model development. Model performance depends heavily on feature engineering, algorithm selection, and hyperparameter configuration, decisions requiring deep expertise and extensive trial and error. AutoML addresses this through 3 core automation capabilities. Automated feature engineering tries various transformation and combination strategies to discover informative feature representations. Automated algorithm selection compares multiple candidates and recommends the best match for the data and task type. Hyperparameter optimization efficiently searches the parameter space using strategies like Bayesian optimization. The output is a fully optimized, deployment-ready model. AutoML substantially lowers the barrier for teams without deep ML expertise, while saving expert practitioners significant time on repetitive tuning. Distributed training is the core technology enabling large-scale deep learning model training at practical timescales. TI-1 provides comprehensive distributed training support, allowing users to train large models efficiently across GPU clusters. TI-1 supports 2 primary distributed paradigms. The parameter server architecture stores model parameters centrally, with multiple worker nodes processing data batches in parallel and synchronizing through push and pull operations, advantageous for models with very large parameter counts. The all-reduce architecture uses high-performance communication libraries like NCCL for direct gradient aggregation across worker nodes with higher communication efficiency, optimal for dense GPU cluster configurations. The core value is near-linear training acceleration. Using NGPUs reduces training time to approximately 1/n, turning weeks of computation into days and dramatically accelerating iteration cycles for large-scale model development. Model evaluation is a non-negotiable step in the training workflow, determining whether a model has earned the right to be deployed in production. TI1 provides comprehensive evaluation tools supporting multidimensional performance metric calculation and visualization. For classification tasks, core metrics include accuracy, correctly classified samples, precision, true positives among predicted positives, recall, actual positives correctly identified, and F1, score, the harmonic mean of precision and recall as a balanced performance measure. The confusion matrix reveals prediction distributions across classes, intuitively identifying where the model conflates categories. ROC curves and AUC values provide comprehensive performance views across decision thresholds, with higher AUC indicating stronger discriminative ability. Model quantization is an important post-evaluation optimization step. Compressing floating point parameters substantially reduces inference latency and model size, a necessary pre-production step. Model deployment is the critical step transforming a trained model into an online service callable by business systems. The final mile, delivering commercial value from a machine learning project. TI1 offers multiple flexible deployment options. REST API deployment wraps the model in a standard HTTP interface, supporting HTTPS and gRPC, suitable for most business integration scenarios. Batch inference serves high-volume offline prediction scenarios that do not require real-time response and efficiently utilize off-peak compute capacity. A/B testing deployment runs two model versions simultaneously, routing requests by configured traffic splits to compare real-world performance before a full switch, the best practice for safely validating model updates. Canary releases route a small traffic fraction to the new version and gradually scale after thorough validation. The prudent approach for high-risk service updates. Inference performance can be further enhanced through TensorRT and ONNX runtime optimization. TI1's online inference service receives external requests, routes them to appropriate model instances, and returns predictions, requiring a precise balance between high availability and low latency. Key features include high availability API interfaces supporting RESTful and gRPC with a 99.99% SLA commitment, auto-scaling that adjusts instance counts and compute resources based on real-time QPS load, scaling up during peaks and down during quiet periods. A/B testing support running different versions simultaneously with customizable traffic splits for real traffic validation, and high-performance inference through optimization tools that maximize throughput and minimize latency. Together, these capabilities enable TI1 online inference to support the demands of large-scale production AI applications. This slide explains the standard LLM training workflow on the TI1 platform. We begin with a base model, which already has general language understanding. Next, we perform post-pre-training, where the model is further trained on large volumes of domain-specific, unstructured data to inject specialized knowledge, such as finance or healthcare. After that, we apply supervised fine-tuning, or SFT, using high-quality prompt response pairs to align the model with human intent and task requirements. This step is critical for building chatbots and task-oriented systems. Finally, the trained model is deployed for real-world applications, balancing both domain expertise and instruction-following capability. TI1 ships two first-class inference engines behind the same service abstraction, so teams pick the engine that fits the workload rather than retooling the application. VLLM relies on page detention and continuous batching to squeeze throughput out of a GPU, which is exactly what general chat and large-scale model serving need. SGLang leans on radix attention and prefix caching, which makes it far more efficient when prompts share long system instructions or when requests move through multi-turn agent flows and structured JSON outputs. From an operator's point of view, the model, the endpoint, and the monitoring surface stay identical, and the framework becomes a tuning knob rather than a migration project. Model monitoring is an essential operational capability for production ML systems, an area many teams underinvest in initially, only to pay costs through production incidents later. TI1 model monitoring provides multi-dimensional production observability. API performance monitoring continuously tracks QPS, P99 response latency, and error rates for online services, enabling timely anomaly detection with automated alerting. Model quality monitoring uses feature drift and concept drift detection to identify early signals of model performance degradation. Feature drift occurs when the statistical distribution of input data changes, often predicting an accuracy decline. Concept drift occurs when the relationship between features and labels changes, meaning learned decision patterns no longer apply. When drift thresholds are exceeded, the system automatically triggers human review or retraining workflows, ensuring sustained model quality in production. For large model serving, 3 metrics matter far more than average QPS. TTFT captures how long a user waits before the first token appears and directly shapes perceived responsiveness, so we usually hold it under 1 second for interactive scenarios. ITL measures the gap between consecutive tokens and decides whether streaming output feels smooth or stutters, with 50 milliseconds as a healthy ceiling. TPM reflects total throughput and feeds capacity planning, quota control, and cost attribution. In practice, we alert on P90 and P99 rather than the mean, correlate TPM with spend, and trigger graceful degradation whenever IDL starts drifting before users notice. This case shows TI1 applied to retail inventory optimization, a domain where even small accuracy gains translate into significant margin. The retailer was running on static rules, reorder points set by category, seasonal overrides entered by hand, which led to chronic overstock on slow movers and stockouts on hot items, with compounding waste and lost sales. The team rebuilt the forecasting stack on TI1, fusing historical sales, weather data, promotion calendars, and holidays into a feature pipeline, then training gradient-boosted and sequence models with distributed training to handle hundreds of thousands of SKUs. Predictions feed a replenishment engine that adjusts orders dynamically, replacing the old rule book. The transformation is visible in the headline metrics. Demand forecast accuracy climbs, inventory holding costs drop, and out-of-stock rates fall sharply. Equally important, the platform supports continuous retraining, so as shopping patterns shift, think live streaming spikes or sudden category trends, the model adapts within days rather than quarters. Computer vision quality inspection is a high-value TI1 application in manufacturing, demonstrating deep learning's power on visual data. A factory needs visual quality checks on production line products. Manual inspection is slow and accuracy degrades over time. The team built an AI visual inspection system on TI1, data preparation and model design in Notebook, training a convolutional neural network on PyTorch using annotated product images to distinguish defect-free from defective products. After training and evaluation, deployed as an online inference service integrated with the production line's camera feed for real-time inspection. Results showed a 5x improvement in inspection speed alongside 99.5% accuracy, substantially outperforming stable manual inspection rates. The AI quality inspection system continuously improves through ongoing data accumulation, creating a positive data flywheel effect. These best practices are what distinguish teams that get value from TI1 in weeks from teams that spend months fighting the platform. Start with resource optimization. Right-size instances based on real utilization, not headroom guesses, and use GPU sharing and virtualization for lightweight inference, so you are not paying for an H800 to serve a small model. Autoscale inference clusters on request volume rather than provisioning for peak 24/7. On the data side, treat feature engineering as a first-class deliverable with version feature stores, not ad hoc notebooks, and keep training data lineage explicit so every model can be traced back to its source. For model lifecycle, standardize on a registry, enforce approval gates before production promotion, and automate retraining triggers from drift detection rather than waiting for incidents. Finally, invest early in monitoring. API latency, model quality, and cost dashboards should exist before the first model goes live, not after the first outage. These are not exotic practices. They are the operational hygiene that separates pilots from platforms. Let us consolidate Module 4. This module gave us a comprehensive view of TI1's complete capability system, covering the full chain tools needed for enterprise custom AI model development. We covered the overall architecture from infrastructure through core services and end-to-end MLOps workflow support. We examined notebooks, cloud-optimized features, explored training pipelines, and AutoML, studied distributed training principles, covered model evaluation metrics and quantization optimization, and explored production-grade capabilities, including online inference, batch processing, and model monitoring. Through recommendation system and vision quality inspection case studies, we saw TI1's path from AI capability to real business value. Next, we enter Module 5, CodeBuddy, the AI intelligent coding assistant for developers. Welcome to Module 5, CodeBuddy. If previous modules addressed how to use Tencent Cloud AI services to build products, CodeBuddy tackles a more immediate question: how to make the building process itself dramatically more efficient. CodeBuddy is Tencent Cloud's AI-powered intelligent coding assistant, deeply integrated into mainstream IDEs, including VS Code and JetBrains, covering the full software development lifecycle. It is not simply a code completion tool. It is a comprehensive development intelligence agent that understands context, assists with code generation, identifies bugs, explains code logic, and performs code review. This module covers CodeBuddy's core capabilities, including intelligent code completion, AI code generation, code explanation and refactoring, bug detection, and the technical implementation of deep IDE integration, with concrete case studies. CodeBuddy is an AI-powered coding assistant that works directly inside the developer's IDE. It connects to an LLM backend through a plugin to provide real-time code suggestions. It supports key stages of development like coding and testing, helping developers work faster and more efficiently. Core features include smart code completion, generating code from natural language, and automatic documentation. It also helps with code review, understanding large code bases, refactoring, and bug fixing. Overall, CodeBuddy improves productivity, code quality, and reduces development effort. CodeBuddy is positioned as the AI partner throughout the software development lifecycle, systematically integrating into every phase from requirement understanding through design, coding, testing, debugging, and code review. In requirements analysis, it helps interpret and decompose requirement documents. In coding, it provides context-aware completion and generation to reduce repetitive work. In debugging, it identifies bug patterns and security vulnerabilities with fix recommendations. In testing, it automatically generates unit test cases to improve code coverage. In code review, it analyzes code quality, readability, and potential risks. CodeBuddy supports dozens of major programming languages, including Python, JavaScript, TypeScript, Java, Go, and C++, delivered through IDE plugins so developers benefit from AI assistance within their familiar environments without tool switching. Code completion is CodeBuddy's most frequently used capability. By understanding the current file's contextual information, it predicts what the developer is most likely to write next and offers suggestions at line or function-level granularity. Compared to traditional IDE completion, CodeBuddy differs in three key ways: semantic context understanding, genuinely grasping the logical intent of current code rather than relying only on lexical analysis, cross-file awareness, referencing other project files, dependencies, and code style, and multi-line large-scale generation, predicting and generating entire code blocks or complete function implementations. The tab key acceptance interaction is seamlessly smooth, allowing efficient coding with minimal mental flow interruption. Data shows developers using CodeBuddy achieve over 30% improvement in coding efficiency on average. Code generation takes CodeBuddy's assistance a step further than completion. Developers describe requirements in natural language, and CodeBuddy generates corresponding complete code implementations. This description-to-code workflow enables rapid translation of ideas into executable code, particularly suited for algorithm implementations, data processing routines, and file operations with clear logical structures. Generation quality depends substantially on prompt clarity. Explicitly specifying input and output types, error handling requirements, and performance constraints significantly improves usability. Generated code should be treated as a starting point that the developer reviews and adjusts appropriately before incorporating into the codebase. This human-AI collaboration model leverages AI's generation capability while preserving the developer's final control over code quality. Code explanation is a key capability of CodeBuddy, designed to help developers quickly understand complex or legacy code. Instead of manually analyzing unfamiliar logic, developers can get instant, AI-generated explanations directly within the IDE. The system breaks down code into clear sections, including function purpose, parameters, and logic flow. This is especially useful when working with undocumented or older code bases. It accelerates onboarding for new team members, reduces the risk of errors during modifications, and helps maintain better documentation. Overall, CodeBuddy transforms hard-to-read code into easy-to-understand insights, improving productivity and collaboration across development teams. Bug detection and fixing is a core CodeBuddy code quality capability, proactively identifying potential issues, logic errors, security vulnerabilities, performance problems, and style violations, and providing specific fix recommendations. This shifts problem detection from runtime discovery to right-time identification, dramatically reducing the risk of bugs reaching production environments. For SQL injection detection, CodeBuddy recognizes dangerous string concatenation patterns for SQL construction and prompts use of parameterized queries, a fundamental secure coding requirement. For performance optimization, it identifies common anti-patterns like unnecessary database queries inside loops, suggesting language feature optimizations. By integrating CodeBuddy into IDE workflows and CI/CD pipelines, teams establish a proactive code quality defense layer that catches most avoidable issues before code merges. CodeBuddy's broad language support covers the full programming ecosystem from data science through backend services, front-end development to systems programming. In data science and AI, deep support for Python, R, and Julia with context-aware completion for major libraries, including NumPy and Pandas. For backend development, Java, C++, C#, and PHP with understanding of major framework APIs and design patterns. For front-end and web, JavaScript, TypeScript, and HTML/CSS, including component logic generation for React and Vue. For general and systems programming, Go, Rust, SQL, and shell scripts. Broad language support makes CodeBuddy a unified AI assistant for the full technology stack. Enterprise teams do not need to maintain separate AI tools for different languages, reducing management overhead while delivering consistent experience. CodeBuddy works as an IDE plugin and integrates directly into developers' daily coding tools. This is a key advantage over standalone AI tools. With deep IDE integration, AI Assistance appears naturally in the workflow. No need to switch windows or copy and paste code. Everything happens inside the editor. Technically, the plugin uses LSP, Language Server Protocol, to get code context and an API client to securely connect to the CodeBuddy Cloud AI service. Responses are shown as inline suggestions, sidebar panels, or chat interfaces. CodeBuddy supports major IDEs like VS Code, IntelliJ IDEA, PyCharm, and Visual Studio. For enterprises, it also offers local inference, no code uploaded to the cloud, and supports internal network deployment to meet strict data security requirements. Getting the most out of CodeBuddy is less about the tool and more about how you interact with it, which is why mastering the prompt and context loop is the single highest leverage habit to develop. Be specific in your prompts. Describe the input, the expected output, edge cases, and any constraints explicitly, because vague prompts produce plausible-looking but wrong code. Provide enough surrounding context by keeping relevant files open, pinning key references in the chat, and using inline comments to signal intent, since the model can only reason about what it can see. Iterate in small steps rather than asking for one giant block. Review and refine each generation. Feed errors back into the next prompt, and let the loop converge on a solution you actually understand. Use the shortcuts and / commands to stay in flow. Accepting, rejecting, or editing suggestions should cost a keystroke, not a mouse trip. And treat AI output as a strong draft, not ground truth. Run the tests, read the diffs, and own the final code, because that is how AI assistance turns into genuine productivity rather than technical debt. Enterprise-grade AI coding assistance must satisfy stringent data security and compliance requirements beyond efficiency. CodeBuddy provides a multi-layer security framework. For data transmission, TLS 1.3 encryption protects all data in transit from interception or tampering. For network isolation, VPC private network deployment allows configuring CodeBuddy traffic through enterprise private networks without traversing public networks, meeting strict isolation requirements in finance and government industries. For access control, multi-factor authentication and role-based access control ensure only authorized personnel access functionality. For compliance certification, CodeBuddy has achieved ISO 27001 and SOC 2, providing the compliance endorsements required for enterprise procurement. For organizations with the highest code security sensitivity, a private deployment option keeps source code processed entirely within the corporate network perimeter, maximally protecting code assets. CodeBuddy also supports team collaboration, not just individual productivity. Shared AI configurations allow teams to use the same prompts, context settings, and AI behaviors, which helps maintain consistency and reduce onboarding time. Standardized styles ensure that code generated by AI follows the organization's coding rules, naming conventions, and architectural patterns automatically. In addition, team analytics provide visibility into AI usage, productivity improvement, and code generation trends across projects and developers. Together, these features help development teams work in a more consistent, measurable, and scalable way while improving collaboration and overall engineering efficiency. This slide presents a before and after comparison showing efficiency and quality improvements CodeBuddy delivers in enterprise development teams. Coding time decreases from 100 units to 75, a 25% saving, primarily from code completion and generation, reducing repetitive coding work, especially boilerplate, test code, and documentation generation. Bug volumes decrease from 100 to 60, a 40% reduction, resulting from the coordinated effect of bug detection, code review, and security scanning intercepting more issues before code merges. Notably, junior developer code quality improvement is particularly pronounced after CodeBuddy introduction. AI Assistance effectively provides every new team member with an experienced code review partner delivering continuous real-time quality feedback, accelerating their technical development curve. These quantified ROI figures provide technology decision-makers with direct empirical evidence for evaluating tool adoption. Let us consolidate Module 5a. This module systematically introduced CodeBuddy's complete AI coding assistant capability portfolio. We understood CodeBuddy's positioning spanning the software development lifecycle, not just code completion, but a comprehensive AI development agent covering coding, debugging, testing, and review. We explored the 5 core capabilities in depth: code completion, code generation, code explanation, bug detection, and AI chat. We covered broad programming language support and deep IDE integration with VS Code and JetBrains. We examined enterprise-grade security and compliance and quantified ROI metrics. The final module explores WorkBuddy, how AI fundamentally transforms enterprise knowledge work and collaboration patterns. Welcome to the final module, WorkBuddy. If CodeBuddy is the AI productivity tool for developers, WorkBuddy is the AI intelligent work platform for the entire enterprise, extending AI assistance value to every knowledge worker. WorkBuddy is an enterprise intelligent work platform powered by Tencent AI, supporting multimodal content understanding and generation, and deeply integrating with enterprise CRM, ERP, and OA systems through APIs to break down workflow information silos. This module covers WorkBuddy's core capabilities: multi-format document processing, knowledge base and RAG retrieval, intelligent meeting assistant, and workflow automation integration with enterprise systems. with case studies showing how WorkBuddy improves efficiency and knowledge flow in real enterprise contexts. WorkBuddy is positioned as the enterprise AI knowledge assistant, processing multi-format documents and multimodal content, embedding AI analytical capabilities directly into enterprise daily workflows. 4 core capability dimensions cover the main scenarios of enterprise knowledge work. Document intelligence supports content understanding, key information extraction, and summary generation for PDF, Word, Excel, and other formats. Knowledge-based management consolidates dispersed knowledge assets and enables RAG-powered precise question answering grounded in internal knowledge. Intelligent communication assistance completes high-frequency tasks, including meeting notes, email drafting, and report generation. IT system integration enables cross-system workflow automation through APIs and webhooks. Hunyuan AI serves as the underlying engine, providing stable language understanding and generation across all capabilities. WorkBuddy's document processing is one of its most frequently used capabilities in enterprise office contexts. In modern workflows, employees deal daily with large volumes of PDFs, Word documents, and Excel files. Traditional handling requires reading each individually in manual organization, which is inefficient. WorkBuddy provides a 3-step intelligent document processing workflow. Step 1 is upload and import, supporting major formats including PDF, Word, and Excel with web URL input for intelligent extraction of web content. Step 2 is AI analysis, applying Hunyuan AI for deep content understanding, completing full document summary generation, key information extraction, data table parsing, and perspective organization. Step 3 is structured output, presenting results in clear formats with export support for Markdown, Word, and other formats for direct downstream workflow integration. Document processing is not simple text extraction, but genuine semantic understanding, capable of answering questions requiring reasoning, such as what the core conclusions of a report are or which contract clauses warrant special attention. Knowledge base and RAG is one of WorkBuddy's most differentiated enterprise value capabilities. General large language models only have training time general knowledge and cannot answer questions about enterprise internal processes, product specifications, or historical cases. Meeting intelligence is one of WorkBuddy's most representative enterprise daily efficiency applications. Traditional meeting efficiency losses manifest in 2 ways. Designated note takers divert attention from participation, and post-meeting minute preparation is time-consuming with inconsistent quality. WorkBuddy fully automates this workflow through the combination of ASR transcription and LLM analysis. After meeting recordings are uploaded, ASR completes full transcription with speaker differentiation. The LLM then deeply analyzes the transcript, automatically identifying meeting themes, key discussion points and decisions, action items with responsible parties and deadlines, and unresolved issues and risks. The output is a clearly structured, information-complete meeting minutes document, consistent quality, and extremely fast to generate. For high meeting frequency enterprise teams, meeting intelligence saves note-taking time and, more importantly, improves execution, tracking efficiency for decisions and action items, converting meeting outputs into genuine realized value. Enterprise knowledge management is one of WorkBuddy's most immediately impactful use cases. Before WorkBuddy, a typical enterprise faces the challenge of severely dispersed knowledge. Wikibases, OA systems and departmental folders operate in silos. Employees spend significant time on retrieval, and results are often outdated or lacking context. WorkBuddy transforms this by integrating dispersed knowledge assets into a unified enterprise knowledge base and enabling precise question answering through RAG technology. After introduction, employees ask questions in natural language. The system retrieves the most relevant content from the integrated knowledge base and generates accurate, source-cited answers. Quantified results show a 60% reduction in knowledge retrieval time and a 30% improvement in satisfaction. The deeper value goes beyond these efficiency metrics. It makes organizational knowledge genuinely flow and be reused, reducing knowledge loss for personnel turnover and improving team-wide knowledge sharing. Workflow automation is WorkBuddy's capability for extending AI from a point tool to system-level intelligence, enabling AI to span different business systems and create value at a larger dimension. WorkBuddy implements workflow automation through the chaining of three elements: trigger, AI decision, and action. The trigger element defines what event initiates the workflow: receiving a customer email, a new opportunity in CRM, or a monitoring alert. The AI decision element analyzes triggering event content and judges next actions, classifying customer email intent, assessing opportunity priority, or evaluating alert severity. The action element automatically calls pre-configured APIs to complete business operations, updating CRM records, sending notification emails, or triggering ticket creation. This perception think act automation pattern enables WorkBuddy to serve as an intelligent middleware layer connecting different enterprise systems to achieve automated intelligent operation of complex business processes. WorkBuddy's system integration capability supports seamless connection with enterprise existing information systems through multiple methods, breaking down information silos and extending AI capabilities across the enterprise digital ecosystem. Integration methods include RESTful API direct connection for customized integration by technically capable teams, webhooks for event-driven real-time data synchronization, and OAuth 2.0 and SSO single sign-on meeting enterprise identity authentication security requirements. Typical integration system categories include CRM systems for intelligent customer analysis and sales process automation, ERP systems for AI-assisted analysis of procurement and financial data, and OA systems to improve approval workflows and scheduling intelligence. WorkBuddy's positioning is not to replace existing enterprise systems. It adds an AI intelligence layer on top, generating greater value from existing digital investments. This is a low-risk, high-return AI adoption path. WorkBuddy's security architecture employs multi-layered defense in-depth design, building comprehensive enterprise-grade security from access control through application security, data protection, to infrastructure. Access layer security uses IAM identity management, MFA multi-factor authentication, and RBAC role-based access control in combination, ensuring only verified authorized users access systems and data. Application layer security provides API protection, WAF web application firewall, and DDoS defense. Data layer security is the most critical protection. All data at rest encrypted with A.E.S. -256, all data in transit protected through TLS and SSL, providing end-to-end encryption throughout the complete data lifecycle. Infrastructure layer provides protection through VPC network isolation, dedicated deployment environments, and multi-region disaster recovery. For compliance, WorkBuddy has achieved ISO 27001 certification and data governance compliance requirement, meeting international enterprise client compliance review requirements. This comprehensive security architecture is the important foundation of WorkBuddy's enterprise trust building. This case captures how WorkBuddy transforms the document review bottleneck that plagues so many knowledge work pipelines. The customer, a services firm, was burning analyst hours on manual review of contracts, reports, and regulatory filings, delaying project timelines and consuming senior reviewer capacity on repetitive extraction work. WorkBuddy was deployed as the first-pass reviewer. Documents land in a watch folder or via integration. WorkBuddy extracts key clauses, flags risks, summarizes the material points, and generates a structured review brief in minutes. Human reviewers no longer start from a blank page. They validate, adjust, and sign off, which is a fundamentally higher value task than rereading the same contract template for the 100th time. The measurable outcomes speak for themselves. Review turnaround time collapses, throughput per analyst rises sharply, and the error rate drops because the AI catches mechanical inconsistencies the human eye tends to miss after a long day. The broader lesson is that WorkBuddy does not replace expert judgment. It clears the low-value friction that was consuming expert time. Smart Customer Service is an important WorkBuddy application in enterprise external service contexts. Building an AI customer service system capable of providing professional, consistent, round-the-clock service by integrating product knowledge, service procedures, and frequently asked questions into the WorkBuddy knowledge base. Traditional customer service faces three core tensions: the gap between slow peak period response and user expectations of immediate replies, the mismatch between limited agent knowledge and the diversity of user questions, and the conflict between high human service costs and enterprise scaling requirements. WorkBuddy Smart Customer Service addresses these by building a deep knowledge base from product documentation, FAQs, and historical service records, delivering 24/7 question answering service, where over 50% of queries can be fully handled by AI, with remaining complex or emotionally sensitive questions routed to human agents. Results show a 50% satisfaction improvement and a 35% CSAT uplift. Smart customer service is not about replacing humans. It is about allowing agents to focus on complex issues genuinely requiring empathy and judgment, while AI efficiently handles high volumes of standardized inquiries. Let us consolidate Module 5B, the final module of the complete course. WorkBuddy represents the comprehensive landing of AI in enterprise office contexts, extending AI capabilities from technical teams to every knowledge worker. In this module, we covered WorkBuddy's 4 core capabilities: multi-format document intelligent processing, RAG-based enterprise knowledge-based question answering, intelligent meeting and communication assistance, and enterprise system workflow automation integration. Through knowledge management and smart customer service case studies, we saw how AI assistants generate measurable efficiency and quality improvements in real enterprise operations. We also examined WorkBuddy's security architecture and system integration capabilities, understanding the security and compliance requirements enterprise AI tools must satisfy in production environments. WorkBuddy and CodeBuddy together form 2 important pillars of Tencent Cloud's AI productivity tool portfolio, one facing developers, one facing the entire enterprise, jointly driving the deep application of AI across all work contexts. Tencent Agent Development Platform, or ADP, provides an end-to-end architecture for building AI agents. It connects foundation models with key modules such as the Agent Builder, Knowledge Base with RAG, Workflow Engine, and Plugin Marketplace. This architecture enables businesses to rapidly develop intelligent applications like copilots, customer service systems, and analytics tools. With visual design and modular components, ADP simplifies development while ensuring scalability and security. It allows enterprises to integrate AI seamlessly into their existing systems and workflows. ADP supports a clear end-to-end workflow, starting from agent design, followed by knowledge-based configuration, workflow building, testing, and deployment with monitoring. This structured process ensures faster development and reliable performance. Key features like RAG integration improve response accuracy, while multi-agent collaboration enables handling complex tasks. Best practices include defining clear agent roles, optimizing knowledge-based structure, and performing thorough testing before deployment. Together, these capabilities help enterprises build scalable and production-ready AI solutions efficiently. Now let's look at how to pick the right AI production tool for the job. We have 3 products on the table: CodeBuddy, WorkBuddy, and ADP, and each one targets a very different workflow. CodeBuddy is a coding assistant. Its sweet spot is development, code generation, debugging, unit testing, and refactoring. The primary users are developers, DevOps engineers, and architects. It plugs directly into the IDE through VS Code extensions, connects to Git platforms, and fits natively into CI/CD pipelines. Customization here is high because the tool indexes your code base and builds context-aware prompts, so its suggestions actually reflect your project, not generic boilerplate. WorkBuddy sits on the productivity side. Think content creation, email drafting, meeting summaries, and knowledge retrieval. The audience is broader: business users, product managers, HR, and sales teams. It integrates with IM tools like WeCom, Office Suites, and meeting software, so it meets people where they already work. Customization is medium. You can adjust prompt templates and style preferences, but it is designed to be useful out of the box without deep configuration. ADP, the AI development platform, is the builder's toolkit. It is for constructing custom AI agents, RAG pipelines, and fine-tune models. The users are AI engineers and data scientists who need full control over model behavior. ADP connects to cloud infrastructure, enterprise data lakes, and exposes an API-first architecture. Customization is very high because the whole point is full model fine-tuning and custom logic. You own the entire stack. The key takeaway is that these 3 products are not competing with each other. They serve different personas at different layers of the organization. The right choice depends on whether your priority is shipping code faster, boosting team productivity, or building bespoke AI capabilities from scratch. Welcome to the final slide of this course. Let us take this moment for a final consolidation and look forward to what comes next. This course systematically built the complete knowledge framework for a Tencent Cloud AI practitioner. Module 1 established our foundational understanding of AI and machine learning theory, developing intuition for how algorithms work at a fundamental level. Module 2 took us deep into large language models and Tencent Hunyuan, mastering the technical nature of LLMs and API integration methods. Module 3 introduced the complete capability portfolio of Tencent Cloud SaaS AI services, learning how to rapidly integrate AI capabilities into business applications. Module 4 walked us through the TI1 platform end-to-end, from data preparation through model training, deployment, and monitoring. Module 5 introduced CodeBuddy for developers and WorkBuddy for enterprise workers, demonstrating how AI productivity tools transform daily work patterns. Learning is the starting point. Application is the destination. After completing the course, the recommendation is to choose one real business scenario and personally try to implement one AI capability from today's learning. Whether calling the Hunyuan API, uploading documents to WorkBuddy, or running a simple training job on TI1. Converting knowledge into practice is the most important step toward becoming a genuine AI practitioner.